Going back to Newton's second law yet again, want to take this a step further. Going back a couple of videos, we saw that we can express Newton's second law in terms of the rate of change of momentum. So F is equal to delta P on delta T. So there's a fairly simple and straightforward explanation in terms of momentum, but we know that momentum is the product of mass and velocity. So that change in momentum can actually be the result of a change in mass or a change in velocity. So we need to expand that a little bit further to find a little bit more detail here. Now this next step is not one that you need to be able to do under exam conditions or anything like that. Just explaining the mathematical process that you would go through, and that's using the product rule for differentiation. So considering that we've got the rate of change of a product, what we would see there is that the force can now be expressed more completely as the mass times the rate of change of velocity plus the velocity times the rate of change of mass. So if that doesn't make sense, just sort of take it on faith that that is the correct mathematical procedure that you would follow to expand this rate of change of momentum even further. So I want to now focus on what's happening with this particular expression. So the first term here is one that we've actually seen before. So it's the original form of Newton's second law that we've already seen. And that's basically saying we're a constant mass. So notice I'm adding the word here now, constant, because the mass of the object's not changing. So that mass is accelerated, and we know that acceleration is the rate of change of velocity over time, so delta V on delta T. So that's our acceleration when an unbalanced force is applied. Now you might look at that and say, well, yeah, that makes sense, that's F equals ma, but what about this second term? You'll notice that if mass is constant, so if we don't have any mass change, then delta m over delta t is equal to 0, and so this second term disappears and we're left with our normal form of Newton's second law being F equals ma. I want to have a look in a little bit more detail at that second term now though. You can see that the second term does deal with the change in mass. So the second term accounts for scenarios where mass is also changing. And we've already looked at one of those as a particular example in class and in a previous video, and that's the case of rocket propulsion. So with rocket propulsion, the mass that we're dealing with is the mass of the rocket and the mass of the fuel, but the fuel gets used up over time and exhaust gases are expelled, and so as a result we see this change in mass. So in this scenario, field is ignited, mass of the system, or the mass that's contained within the rocket, decreases. And so we need to take into account that that final term. So I'll just rewrite that equation to explain it a little bit more clearly in the context of rocket propulsion. So for a rocket, we do need to now consider both of those terms. So F being equal to, I'm just going to expand this out a little just so I can write some notes underneath. So m delta V on delta T, so again the usual expression for Newton's second law, plus V multiplied by delta M on delta T. Now this first term we're familiar with, it's the instantaneous mass of the rocket. So now the mass of the rocket's no longer constant, so the instantaneous mass, so the mass at a given point in time, and the acceleration of the rocket at that point in time is what's represented by this term here. And the second term, so this one here now, is the velocity and rate of mass change, or the rate at which exhaust gases are expelled, so we've now got those two quantities incorporated as well. So the velocity at which the exhaust gases are expelled and the rate at which the mass of the exhaust gases are expelled. Let me just fix that in there. I should say are expelled. So we now have a more complete picture of what's going on when we deal with force and change in momentum, and in particular where we've got a changing mass. Some other scenarios where you might consider a changing mass, similar to the ones that we that I alluded to a video or two ago, we could look at that scenario with a helicopter hovering. So you've got a mass of air that's being pushed down. So the mass isn't constant in that case. We need to incorporate that second term. And the other example would be a fire hose. So we'd talk about the rate at which water is being expelled from the end, and also the mass of water that's being expelled as well. So there's, like I say, a fuller and more complete picture of Newton's second law in terms of momentum.